Welcome to Boson Buzz, where we dive into the coolest scientific ideas and breakthroughs shaping tomorrow's world. The power of invisibility is one of humanity's oldest and most persistent dreams, a concept that has captivated our imagination from the myths of ancient Greece to the pages of modern science fiction and blockbuster films. It represents the ultimate form of stealth, privacy, and mystery, the ability to vanish from sight. For centuries, this idea remained firmly in the realm of fantasy, a trick of magic, or advanced alien technology far beyond our grasp. But what if the key to invisibility wasn't a spell or a force field, but a new type of substance engineered by humans? A material that could be designed not for its strength or its flexibility, but for its ability to command the very essence of vision, light itself. This is the revolutionary promise of metamaterials, a field of science that is bringing the dream of the unseen out of the shadows of fantasy and into the harsh, focused light of laboratory reality, challenging our fundamental understanding of physics. To understand how we can make something invisible, we must first understand precisely why we see it in the first place, which comes down to the fundamental interaction between light and matter. We see an object because light rays, traveling from a source like the sun or a lamp, strike that object and interact with its surface. Some wavelengths of light are absorbed by the object's atomic structure, which gives it its perceived color, while other wavelengths are reflected away. These reflected rays then travel in a straight line into our eyes, and our brain's visual cortex interprets this specific pattern of incoming light as a distinct shape, a color, and a precise location in space. A solid brick wall is clearly visible because it reflects and scatters light in a chaotic, diffuse way, while also completely blocking its path, casting a shadow. If you were to become perfectly transparent, like a flawlessly clean and perfectly flat pane of high-quality glass, light would pass straight through you with minimal distortion and you would be nearly invisible. But making a complex, multi-layered, and opaque object like a person, a tank, or a jet fighter transparent is physically impossible with any conventional natural material known to science. The solution, therefore, is not to try and stop the light from hitting the object, nor is it to make the object transparent. The ingenious solution is to guide the light smoothly around the object, like water flowing seamlessly and without turbulence around the smooth rock in a fast-moving riverbed, and then allow it to continue on its original, uninterrupted path on the other side as if nothing were there at all, leaving no shadow, reflection, or distortion to betray the object's presence. This is where metamaterials enter the story, and they are unlike any substance found in nature. The prefix meta means beyond, and that is precisely what these materials are. They possess properties beyond those of naturally occurring elements and compounds. A metamaterial is not a single chemical, but a composite structure, meticulously engineered by humans. It is built from a grid of microscopic, repeating shapes and patterns, often resembling tiny loops, squares, or intricate circuits that are smaller than the wavelength of the light they are designed to control. By arranging these tiny structures in a specific, precise geometry, scientists can create a material with a custom-made index of refraction, a property that dictates the exact speed and path a light ray will take when it enters the material. This allows them to design a shell, or a cloak, that forces incoming light rays to flow around an object hidden at its center, bending them in a coordinated way and seamlessly reconnecting them on the other side, perfectly restoring the original light field. To an observer, the light appears to have traveled in a straight line, rendering the cloaked object completely invisible. The first successful invisibility cloaks demonstrated in laboratories around the world were not for the narrow band of visible light that our eyes can perceive, but for other, much longer wavelengths on the vast electromagnetic spectrum, such as microwaves and radio waves. Bending these longer wavelengths is a more manageable and practical first step for engineers, because the repeating structures in the metamaterial do not need to be fabricated at an impossibly small nanoscale size. They can be larger and more feasible to create with existing technology. This initial success has profound and immediate real-world applications that extend far beyond the sci-fi dream of mere hiding. For instance, metamaterials are already being used to create sophisticated, radar-absorbing covers for military satellites and aircraft, making them effectively invisible to enemy radar systems and providing a new, critical level of battlefield stealth and security. They can also be used by engineers to design dramatically better wireless routers and next-generation cellular antennas by directing Wi-Fi and 5G radio signals more efficiently around obstacles inside a crowded home or a dense urban cityscape, eliminating dead zones. Researchers in top universities and corporate labs are now relentlessly pushing the boundaries further, successfully creating advanced metamaterials that can work with specific, narrow bands of visible light, such as pure red or pure green, in highly controlled laboratory settings. While a perfect wide-spectrum, Harry Potter-style cloak that hides a macroscopic object like a person from all viewing angles and all colors of light in the bustling, unpredictable real world remains a formidable future goal. The underlying physics principle is no longer a matter of scientific debate. It is a proven, rapidly advancing field of practical engineering and materials science, with new breakthroughs being published on a regular basis. The potential of metamaterials extends far beyond the captivating goal of invisibility, promising to revolutionize numerous technologies. One of the most promising applications is in the field of optics, with the creation of super lenses. Traditional lenses are limited by the diffraction of light, but a metamaterial lens could overcome this limit, allowing us to see details far smaller than a conventional microscope can reveal, potentially observing living viruses or the interior of living cells in real time, which would revolutionize biology and medicine. They are also enabling new types of ultra-thin thermal camouflage that can hide objects from heat-sensing infrared cameras. Furthermore, metamaterials can lead to advanced sensors capable of detecting the faintest traces of a chemical or a biological agent, and could even be used to create more efficient solar panels by controlling how light is captured and absorbed. We are learning that the true power of a material lies not just in what it is made of, but in how we structure it, opening doors to technologies we are only beginning to imagine. The path to perfecting and broadly applying metamaterials for visible light is currently fraught with immense scientific, engineering, and economic challenges that researchers are diligently working to overcome. The primary hurdle is one of scale, creating the intricate resonant structures that are smaller than the wavelength of visible light. A scale of just a few hundred nanometers, smaller than most bacteria, requires incredibly precise and exorbitantly expensive manufacturing techniques like electron beam lithography or focused ion beam milling. These are slow, specialized processes that make mass production of large-scale metamaterials currently infeasible and prohibitively costly for any consumer application. Many of the early metamaterial prototypes were also extremely inefficient, absorbing or scattering too much of the light energy they were trying to bend, which would make a visual cloak appear as a dark, shadowy, and highly noticeable patch rather than a perfect window. Another major, fundamental hurdle is the issue of bandwidth. Most metamaterials are painstakingly designed and optimized to work for only one specific color of light or one type of electromagnetic wave, as their structure resonates at a very specific frequency. Creating a cloak that works simultaneously for the entire rainbow spectrum of visible light is an enormous challenge, akin to designing a single musical instrument that can perfectly play every note from a deep bass to a high soprano at the same time. These obstacles are significant, but they are not considered permanent barriers. Instead, they represent the focused, thorny problems that hundreds of research teams around the world are attacking from different angles, driving relentless innovation in nanotechnology, materials science, and optical physics at an unprecedented and thrilling pace. We are at the beginning of a materials revolution. The journey to create a perfect invisibility cloak is, in many ways, a grand challenge that is pushing the entire field of photonics and nanotechnology forward. We are moving from an era of discovering materials to an era of architecting them, of building substances from the atom up to perform specific, once impossible tasks. While a perfect invisibility cloak may still be years away, the impact of metamaterials is already being felt in the technologies they are enabling today, from medical imaging to secure communications. We are not just making objects disappear, we are making old limits to science and engineering vanish. By learning to sculpt the flow of light itself, we are gaining a mastery over our visual world that was once pure magic, proving that the most fantastic dreams can, with ingenuity and persistence, become the foundation for a new reality. If you found this as fascinating as I did, do me a huge favor and hit that like button. Share this video with anyone who loves science or just cool, futuristic tech. And of course, if you want to stay updated on this and other amazing breakthroughs, make sure you subscribe to the channel. Thanks for watching, and I'll see you in the next one.